So this is a reprisal of a talk I gave at the European Lisp Symposium earlier this year. It's just recycling. So, and what happened here? There we go. There we go. So, about me. My name's Ahmon. I've been working at Franz since '95. I was working here at Franz part-time when I was in college, and then kept on working at Franz. When I first started at Franz, I was doing systems administration. So I was the IT guy. And during that time, I wrote lots of software in Common Lisp for SA purposes. A mail server, FTP server, an IMAP server, NFS server for Windows, all in Common Lisp. That was fun.
DevOps in Common Lisp at Franz?
A lot of our DevOps is in Common Lisp, yes. Yeah. So we use all these things in production. Our mail server, if you send us a mail, it's going through our Common Lisp mail server that we wrote. Jans had mentioned our NFS servers used on the Boeing aircrafts for their onboard network system. I don't know what it does. I think it collects diagnostic information and prepares it for maintenance people to download. And then in 2008, I switched over to working on Allegra Graph, which Jans has told you all about. And in particular, I work at what we call the storage layer, which is responsible for saving the triples to disk in a transactional way with all the isolation and durability needs for a real database. As you said, you can add triples, commit, pull the power out of the machine, you boot it back up, those triples are going to be there. So moving on. So this talk is about using Allegra Common Lisp to develop Allegra Graph, some of the things we had to do. Right now, Allegra Graph only works on Linux x86-64, at least the server component. You can connect with various other clients. In particular, this talks about some of the data structures we created that live outside of the Lisp heap. And just as an elementary slide, the heap is the memory area where you allocate objects. You make an array, comes out of the heap. Cons something up, comes out of the heap. So some of the data structures that I created that live outside of the heap, lists, hash tables, arrays, all the things you can think of, sparse bitmaps, memory allocator for out-of-heap allocations, and then we have some very specialized Allegra Graph specific data structures for compressing the triples and things of that nature. So lots of things that are part of Lisp that I re-implemented in Lisp for particular reasons, and I'll discuss the reasons. Yes?
I'm lost here. So you're out of the heap, but if you just allocate it once, you could use heap, no problem.
I could use heap.
So why are you doing this? Oh, okay.
Why am I doing this? Why do we do this? Yeah.
We already got it, wasn't it?
So why do we do this? So one reason is sharing data across multiple processes. So here's we have 3 workers participating in the database. A couple might be doing queries, people asking for triples. One might be committing, worker 3 here in this example. And to perform that function, they need to work on shared data. And so we'll use these various types of data structures to allow them to share. I don't think I have anything specifically to say more about that. Yes, okay. I have my notes here just to make sure I say everything I want to say. All right. Another reason is persistence. So it's a database, right? You want to be able to get your data back. Now, you can implement persistence really easily with standard Lisp objects, right? You can just print them. Most of them have a printed representation that's readable, right? So we could have made a database where we just write things to files in their standard Lisp representation. One data structure that does not have a standard printed representation is a hash table. But we can really easily write some code to save a hash table to a file. So here we just map the hash table, collect the key value pairs into consoles, put them in a Lisp, write the list to a file using the standard printer. So, and the reverse function, read the consoles out of the file, reconstruct the hash table. So we could do this, but that won't scale. The more data you put into it, the longer it's going to take to write that data structure out, the longer it's going to take to bring it back in when you start the program over. So And let's see. And lastly, efficiency. We all know about GC and how GC works, I presume. You allocate your stuff in one area. When it fills up, the live objects are copied to another area, and that happens back and forth. Eventually, things move over into old space where they don't get moved as often, but they'll still get moved. So if you have a gigabyte data structure, you would like to avoid moving it around. We use, we have a database that's designed to hold millions and billions of objects. We don't want to be moving them around so often. So these are our main motivations. Each one individually is not a huge motivator, but together they're a great motivator for making these out of heap data structures. So next I'll talk about some of the means that we use to create these data structures. One of the main ones, memory mapped files. Does everybody know what a memory mapped file is? Okay. Okay. So a memory map, you know what a file is, of course. You know what memory is. You got your program, you have your address space, you can access bytes. A memory mapped file lets you access the contents of a file just by accessing memory. So if you have a file with ABC in it, you can say, operating system, please map this file into my address space. The operating system says okay. It's at address 1000. So if I access byte 1000, I'm going to see my A. Byte 1002, I'm going to see my B. So
is this like a RAM disk of decades ago?
I would not put it in those terms. When I think of RAM disk, I think of something that's volatile. When you terminate it, it goes away. This is file back, so if I actually write back, it's actually going to write back to the file system. So not quite a RAM disk. It's, I guess you could think of it as a RAM disk, which caches the contents of a file.
With a battery.
In some sense, yes. So nice thing about memory mapped files, when you do those memory accesses to access it, if the file's already resident in the operating system cache, very fast access, as fast as it takes to access memory. You're not making a system call to read. Once you just suffer that page fault, when it's first accessed, everything after that is free, almost. As free as a memory access is. And it allows us to let the operating system work for us. So that's really bothersome. All right.
Huh?
That's really bothersome. Anyway, we need to fix
I
that.
have no idea what it's...
So let's say we have a medium-sized file with a bunch of 32-bit integers in it, and we want to read every one. Using standard common Lisp code, which I have here, I have a function that says read USB 32s from a stream, and it just uses standard read byte in a while loop, and doesn't do anything with the data, but does read it. And so I have a test file, I open it, I specify that the bytes are actually 32-bit bytes, and then I read them. And when I ran this on whatever computer I ran it on, which was, I don't know, a Xeon something or other, yeah, a 2.7 gigahertz Xeon, it took about 3.3 seconds to run. So standard Lisp code takes 3 seconds to read 558 megabytes of 32-bit integers. If we memory map the file instead, and the way we do that is to open the file, but we say map to T. We get a stream back, and one element of that stream, one of the slots, is the buffer. And the buffer slot tells us actually where it got mapped into memory. So that we asked the operating system map a file for us. The operating system said, yes, I mapped it here. So now we can access the bytes there. The way we do that is to use an internal function in Allegra CL called memref. Memref, you give it an address, you give it some offsets, you tell it what element type you're accessing, it'll give you the bytes back. So we're saying, hey, I'd like to reference an unsigned log 2 at the base address plus the offset. And so this is just a simple while loop. We start at the 0th offset, advance by 4 because we're using 4-byte integers. So this does the equivalent of that last function we saw. And when I run this, it takes less than a second, so it's about 4 times faster. Very important for a database product to be 4 times faster than standard Lisp code. And if I added a bunch of declarations to this function, declaring the type of offset to be fixed num and stuff like that, it would be about 5 times faster. So it's worthwhile for us to do these kind of things. And okay, so I'm running that same function again, same function from the last slide, with the new time macro, which gives us some more information about what happened. I want to just highlight the fact that we get 142,000 page faults when we do that, minor page faults, which means every time we access a new page of memory, operating system takes a page fault, brings the file data into our address space, and makes it available to us. But even with all that overhead, it's still faster than just reading using the standard Lisp functions. Anybody have any questions? Okay. So given the size of the file, it takes 142,000 page faults to read it.
Any sense how it relates to if you wrote that in C code, do that same loop?
It would be very close. If I added the declarations, if I declared the type of offset, it would be
kind of deal.
it would be very close. Our compiler's really good. It would generate very good code. So memrefs, I've already mentioned briefly. So memref is our instruction to access memory given a base address and some offsets. Here's a description of what we can do with memrefs. So we have two things. We have memref int and memref. I'll talk about memref later. Memref int, you take an address of memory, offset and position. So basically two offsets, and the access type you want to do. So here are some of the types that we support. Pretty straightforward. This one's a little notable. You can say, I'm going to access something that's the natural word size of the Lisp, but constrained to fixed num range. And it allows the compiler to generate more efficient code. Because if you access, let's say you're using a 32-bit Lisp, and you access a 32-bit number, that 32 number is not fixed num, so it might be a big num, and big nums require extra memory and cost to access. So you're going to see me mentioning fixed nums a lot in this presentation because they're very efficient. And another mechanism we use is for instructs. So for example, I have a macro called fdef_struct. And in this example, I'm defining a structure that has two integer components, an x and a y component. When I use this macro, it generates accessors for me. So if I have the address of one of these structs, I can access the y coordinate by asking for, just like a structure access for a standard Lisp object that works the same on an arbitrary memory location. Does that make sense? Cool. You can write to it the same way as you would in a standard Lisp structure slot. And the macro also, gives me some size information. This is two 32-bit words. That's 8 bytes. Cool so far? All right. And just using our test file again and showing how we might actually access. So again, open the file mapped T, grab the buffer slot, which tells us where it was mapped, the address, and then we can access the first two 32-bit words of that file in this manner. Does that make sense? Okay. And it happened to be some random numbers. It was just a random file I picked. And align pointers. This one's a little deep, so you might like it. So let's talk about a 32-bit Lisp because of the numbers are smaller. So if you have a 32-bit pointer, that's going to be a number between 0 and 1 minus 2 to the 32, right? Yes, okay. However, on our 32-bit Lisp, the most positive fixed num, the biggest fixed num you can represent is 536 million, far less than 2 to the 32, right? So what that means, if you do the math, is that only 12% of the address space can be accessed as a fixed num. The remaining 87%, you're going to have a big num representing your pointer. And we don't like big nums. They're consy. They actually take a lot more memory than just your 32-bit pointer. You have to indirect to read them. So you got to read the parts of the big num, reconstruct it, and then use that as your pointer. All that generates more instructions, causes more GCs the more often you use them. If you do any pointer arithmetic, big num plus big num equals another big num. You don't want to do that. So what we do to compensate for that is we use aligned pointers. And an aligned pointer is an address that accesses word size units. So normal pointers point at bytes, right? Aligned pointers point at words. So basically an aligned pointer is an index, a word index into memory. So because of that, they're always fixed num. You can access the entire address space using a fixed num aligned pointer without consing. So at least in Allegra Common Lisp, and I'm guessing this is true in other Lisps, the actual Lisp val, the actual representation of a fixed num is exactly the same bit pattern as the actual pointer you would use in C. So for example, to access the index 1 into memory, when you actually looked at the Lisp file representation of 1, it would actually be 8, which is, or sorry, 4, which is the actual address of the 1th element in the memory. Yes?
So if positive fixed nums gives you only an eighth of the address space,
Yep.
If you restrict all objects or all pointers to be multiples of 4, that still only would give you 50%. Positive fixed nums would fit in.
So
Is there?
Yeah, 4 times.
I didn't quite follow your question.
So we have 12.5% using plain positive fixed nums.
Yes.
And then we restrict everything to be aligned to a multiple of 4.
Oh, you're asking how? Oh, that's a very good. Okay, I got your question.
12.5% of negative fixed nums.
Right. So do you then use negative fixed nums for high addresses, or?
Yes, we do. Okay, I didn't quite catch your. Yeah. So here I actually show the bit representation of what fixed nums are in Allegra Common Lisp. So most positive fixed num actually looks like this. And if you're really nerdy, you recognize this as the word just before the half of the top or the bottom half of address space in 32-bit. And if you get advanced to most, or if you look at most negative fixed num, it's the word just after that. Does that make sense to everybody? So the way this works is the same reason, if you cast an unsigned number to a signed number in C, you may get a negative number, right? So this is a cool trick that we use a lot in Allegra Graph to do fast memory accesses without consing. So now I'm going to discuss how we might implement some of these out-of-heap data structures. Yeah. Okay, I'll just. So this is a call to the fdefstruct macro. We're going to describe how we might make a foreign list. I have an administrative data structure which has a pointer to the head of the list and a counter, just to be interesting. And then we have a list item element, which, by the way, this is a list that only holds fixed nums. As I said, we're going to be doing a lot of fixing
If
stuff.
you escape, try escape to see if it fits on the screen. To hit escape, it gets a little bit.
Oh, that is better. Okay. All right.
Okay.
No, that's much better.
Readable anymore.
Can everybody still read it? Okay, good. So we have, our fake con cell, and which holds the actual value. Yes.
And now drag that thing there.
The slider.
The slider, and you can make it a little bit bigger.
Okay. Tell me when it's.
Yeah, that's
too big.
That's far worse. Yeah.
I think where it was. Well, I'm having a hard time sliding it smoothly.
It's good.
Right there? Is that good? Okay. All right. And standard linked list points to the next item in the list. And if we store a 0 in there, we use that as a null pointer indicating the end of the list. So this list holds fixed nums only. And it's a good time to mention Philip Greenspun's 10th rule of programming, right? Any sufficiently complicated C or Fortran program has an ad hoc, informally specified bug-ridden slow implementation of half of Common Lisp. And Robert Morris added a corollary to it, says even Common Lisp also includes complicated bug-ridden informal, and that's exactly what it is. So implementing Lisp in Lisp is what this is doing. So does everybody understand how we might use something like this? Con cells, head of a list. And some sample code that might add an item to such a list. So we have, this function takes a base address of a memory area. I'm glossing over how we got that address. It takes the aligned pointer to that administrative structure and the value you want to add to the list. I have some declarations here to clarify what these things are. So these two are aligned pointers to their respective data structures. And the value is going to be a fixed num by how we define this thing to be. So how do you add something to a linked list? You get the head of the old list. You allocate a node. We're going to allocate a list item. I'm glossing over how we allocated it. But we allocate one of these. We fill in the data. Let's see, fill in the data with the value. The next pointer of the new node points to the original head of the list. and then we set the head of the list to the new node. Does that make sense? Waving my hands a lot to you. All right, so simple linked list implementation in foreign memory space. And likewise, a popping function, it's mostly the same. One thing I'm glossing over here is the fact that my, actually maybe I say it, no I don't say it. We never actually store, I said, this is a pointer to the next item. It's actually not a pointer, it's a offset from the memory base area to the next item. And the reason I do that is because, one, full pointers would be, I guess I could use line pointers. The reason I don't store full pointers or full line pointers is because when you have different programs, when you ask the operating system to map an area for you, it can put that mapping anywhere. So one program might have it here, another program might have it here. I can't store absolute pointers. Two programs are accessing the same memory, but different addresses. They need to be able to synchronize themselves. So I store offsets and do the computations to compute the offsets. For example, I allocated the node, the list item, got its aligned address back, and I did the computation offsetting from the base address and store the offset.
Just making sure I'm tracking what's going on here. This stuff is fancy stuff you added to Common Lisp so that you could implement Allegra graph efficiently on top of Lisp, and it's doing fancy tricks with memory mapping and that sort of thing. So this is essentially a turbocharged Common Lisp that would let me build things like Allegra graph if that was my goal.
Yes.
That's okay.
That's basically
okay,
that's what this talk is. Yeah.
Built an external heap.
I built an external heap. Exactly.
Now I get it.
Yes.
I have been talking to Ahmon about writing a book about because he did so many of these structures that it almost requires a book where he describes efficient techniques to deal with a real-time system or whatever.
I get it, yeah.
Yeah, it's an idea.
One thing I didn't mention in an earlier slide, which is in the motivation slide, we could share amongst processes by using a single Lisp with multiple threads and having them all share with each other in the same address space, and that becomes a lot simpler. But at the time we started writing Allegra graph, we did not have a true SMP Lisp, multiprocessing Lisp. If one thread was running, the others weren't running. And we couldn't have that for a concurrent high performance database. So instead, we actually run separate OS processes, and they share the memory using these techniques.
We do it now, but we still like this for stability.
And there are other advantages too. For example, if you have all threads in the same Lisp, if one triggers a GC, they all stop. Everybody waits until that GC is done. Another reason where it's two separate Lisps, this one has a GC, this one keeps on trucking. So
Who GCs your stuff?
that is our stuff. Who GCs my stuff? Right. So I'll talk about that. Nobody is the answer. You do, the programmer does. So a popping function, I'm not going to go into detail there. Here's another type of data structure we might use, file back to global array. Just something you add. You can index and get bytes back. And so I define an administrative structure again, called a mem array, which can hold the file name of the file that's backing the array, the element size, and the open stream, and the size of the mapping, the current size of the mapping. So here I show an example of making one of these mem array structures. Yeah. So I say I'm going to map this test file, and my elements are 12 bytes apiece. So it's an array of char 12. Does that make sense? Okay. And I call the mapping function, which is listed here. So what I do, once again, open that stream, map to T. You're going to see that a lot. This function is actually very simple. All it does is hold that stream in the memory structure and keeps track of how large the file was at the time it was mapped. And the reason we do that is so that when you want to set an element, so I want to set an element in this memory structure at index whatever. This is a data agnostic data structure. So you point it at some bytes and it'll copy them for you into the array. So we have a source address of the bytes and a source offset. This is a line pointer again. So as you might expect from a function that manipulates an array, we get the element size. We multiply the index by the element size to actually get the offset within the array where the byte should go. We compute the end offset, the end of the bytes. And if we find that the end offset is bigger than the current size of the mapping, we need to grow the array. And I'll show the growing function in the next slide. But assuming everything fits, once again, we grab the stream, we get that buffer slot to get the base of the array, and then we just use a fictional memory copy function. Copy to the base address of the array at the computed offset using the source material and copying element size number of bytes. Everybody following me? Good? Okay. Here's the growing function, pretty straightforward. We take the new size and I could have left it just taking new size and increasing the file size that way, but actually what we do is we double the size of the file. We take the larger of double the size or the new size. That way we're not constantly, repeatedly extending the size of the file. So we compute the new size, grab that stream. We call the ftruncate system call to say, operating system, make this file bigger. And we close the stream and then remap it, reopen it to get the new mapping. Because operating system mapped the file into memory, there might be something right after that mapping. It can't necessarily just make it the mapping larger. It might have to move it to a different spot. So we have to close it and reopen it, remap it basically. Clear? All right, good. Okay, so now shared memory hash table implementation. This is really simple. The hash table is fixed size, no rehashing, and the values and keys are fixed nums once again. And we do collision resolution by probing. How many of you have implemented a hash table? Okay, so this will be familiar. So hash tables are, of course, a bunch of slots with keys and values in them, right? I show some of the values that this fdefstruct macro creates. I'm assuming a 32-bit Lisp, so 2 fixed nums is 8 bytes in size. And this one's a little hard to explain, but since the aligned unit is the same size as a fixed num, this data structure is 2 aligned units in size. So, because it's 2 fixed nums. So if I have a base address and I add 2 to it, I'm going to be pointing to the next slot. This data structure also steals part of the fixed num space to indicate unused slots. So we steal most positive fixed num. You won't be able to add that to your hash table. Here I have a function like all the other ones. We assume in this case that we already have a backing file. We open it mapped, and then we make a structure to hold information about the number of slots and hold the stream. So that gets us set up. And here's a function we might use to initialize this hash table. Grab the stream, get the base address of the mapping of the stream. For each slot, compute the address of the slot, which is the base address, the slot number multiplied by the align size. And then we just fill in all the slots we fill the key portion of each slot with the unused indicator. Make sense? Okay.
You would on the map, you would have one file per hash table that you end up using. You essentially have built it in a way that you always have one file entirely dedicated to that hash table.
In this case, yes, you could do that. You could certainly put multiple hash tables, multiple fixed size hash tables in a single file. You would just have a different, have a new base, right? Yeah. So.
This is just a simple example.
These are all trimmed down, simple. Like for example, I glossed over locking and concurrency in the list. You'd have to add all that for real concurrent access. That would be too big to put on the slides. So. But yeah, all that has to be in there, and it's definitely in there in our actual code. So here's a helper function which searches for a key in the hash table. We grab the base address of the hash table. We find out how many slots are in the hash table. We call a fictional hash function on the key, mod it with the number of slots. That gives us our starting slot number. And then we just compute the address of the slot, grab the key from the slot that we're looking at, the key match, then we found it. We return true to indicate we found it, and we also return the slot so that the functions that use this helper can manipulate the slot.
You say fictional because it's macro expanded or what?
It's fictional, that it could be, it's whatever it is. It doesn't matter what it is for the purposes of this discussion.
Oh,
Okay.
you would insert whatever
Yes.
happened to be, okay.
It would be, hypothetical maybe is the word I should have used. If we land on an unused slot, we stop the scan. We return nil to indicate we did not find the key we're looking for, but we return the slot in case we want to use that when we're inserting. Otherwise, we advance to the next slot, wrapping around if we hit the last slot. And if we can't find it after looking at all the slots, that means 1, the hash table is full, and 2, we definitely did not find the key we were looking for. So here's how we might use that helper function, which I called htsearch, to actually implement a insertion function. So I want to put a key and a value in the hash table. So I call the searching function. It returns information about whether the key was already there, which is the found. It'll be T or nil. So it does a search for us. If it found an existing key, we just update the value slot because it returned the slot that we could manipulate. If it was not found, but we got a slot back, we know we can use that slot to insert our new value, our new key and value. Otherwise, the hash table's full and you couldn't have inserted anymore. And likewise, the retrieval function, find this key in the hash table. We call the same searching function. If it says it was found, we return the value portion of the slot. Otherwise, it's not there, return nil.
So your fixed num keys, fixed nums essentially don't have access to the 3 LSBs, which inside of Lisp are usually indicate type.
2 LSBs actually in ours, yes.
Okay, right. But here, as the pointer into, or as the key into that isn't used. You just have fixed nums. Then this means you can't distinguish a fixed num from nil, or you don't distinguish fixed num from nil.
That's right. It's very C-like programming.
Okay.
This is very C, yeah, so I discuss that later. But
If you did distinguish it from nil, then you could allow any fixed num. Because if the fixed num is actually generated by a hash, say as a hash of something more complicated, then you need to allow all values. You can make that exception.
well, the fixed num is not generated by a hash. It's
So it's the, I guess if
it's the
you're,
value that the caller wants to put in there. We just constrain what they can put in.
Yeah.
Let's talk about it afterwards.
Yeah.
Maybe we'll come up with some idea.
That depends on how it's used.
Right. So, yeah, these data structures are constrained in how they're used,
Yeah.
which one gives them their speed.
Yeah.
But in practice, it turns out to be not a problem. Next data structure we might have is a sparse bitmap. In Allegra graph, we use this to note which triples have been deleted. We set a bit in a bitmap to indicate a triple's been deleted. Because triples have an ID number, as we discussed earlier, right? So we set the ID number bit in the bitmap to indicate deletion. So, we have a constant for the number of bits in a word. We have a function that will give us, given a bit number, it'll give us the word that bit is in and the index within that word that the bit is in. So if we pass a 0 in here, we're going to get 0 and 0 back. If we pass, assuming an 32-bit Lisp, if we pass in a, let's say 33, that's going to be the 1th word, index 1 word, the index 1 bit within that word. Does that make sense? Okay. So to set a memory bit, we have a base address of our bitmap. We have the index that we want to set. We call a function that gives us the word index and the bit index. We compute the pointer to the word, a line pointer to the word. We read the word, and then we use standard Lisp code to set the bit in the word that we read, and then we write it back. Read, modify, write operation. Yes?
On x86, there's a bit test and bit set instruction and so forth. Does the compiler manage to turn this into that, or does it not make a difference?
Our compiler does not do that. It would actually generate.
This is weird.
It is weird. That's annoying. I'm just going to close.
Organizer has ended.
It wasn't us.
Great time.
Yeah, our compiler does not do that. At least not the way I coded this. It's possible that if I did it in some different way, it might.
Let me start it again.
Okay.
Can you say how that's, it doesn't seem to be sparse. That seems to be a full bitmap.
I will talk about the sparseness momentarily.
Okay.
Or what, yeah, none of this has anything to do with being sparse. I'll talk about it in a second.
This is live on GoToMeeting right now?
It's being recorded.
recorded
Yeah.
go-to-meeting mechanism.
Yes, exactly.
So while we're having this interval, I will just say that we're also recording the speaker, and we'll combine those later. And the camera, the microphone are both due to donation by Phil Greenspun.
Ah, we've got some props here, right?
So,
Well, thank you, Phil.
thank you, Phil.
Is that glowing blue apparatus a microphone?
I'm assuming so. Or I hope so.
If the talk isn't good,
That's right. God. All right.
Stop recording. I'm now sharing my screen. Restart recording. Okay.
Good.
I don't know what happened, but it's.
Okay, we back in action. Okay, can you advance to the next slide for me, please?
Mine's there, yours is gone.
Could actually make it even better.
Amazon actually sells.
Just put it back where. Just click on there for me. Just click on there. That'll be good enough. Yep. Okay. Before we go to talk about what actually makes us sparse, I just have the reverse function to clear a bit. It's exactly the same as the other one except for the bit logic that we used at the end. Oh, come on. And again, a function to retrieve a bit. You know, give me the index and tells you whether the bit was set or not. Exact same, just different logic at the end. So, what makes this a sparse bitmap? Well, we use a sparse file. The file that's backing it is sparse. A sparse file is one that has holes in it. Is everybody familiar with sparse files? No, okay. So a sparse file is one that has holes in it. So you can tell the operating system, hey, make me a file that's this big. And what it'll do is say, yeah, it's that big. But it doesn't actually allocate any disk space behind it. It doesn't actually allocate the space until you write to a portion of it. And if you read any portion of it before writing to it, you just get zeros back. Which is what I say here. So, does that clarify things? Okay.
So if you write ones throughout the entire thing,
And it's no longer
allocate
sparse.
everything, and then if you write zeros on the prefix, will it?
No. So as far as I know, no operating. Well, Linux does not say, oh, you're actually writing a bunch of zeros, so I'm just going to deallocate the space. It doesn't do that. There are secret system calls you can make to say deallocate this portion of this file. But we don't use those. But we consider using them for in the future.
The one negative thing is that we get a lot of support calls because if you try to use the regular Linux copy, it suddenly builds a non-existing file in 32 gigabytes.
Yeah, so sparse files can be very confusing because you look at them and their apparent size is very huge. We allocate a 4 gigabyte one. But, you know, so people, yeah, I have this 4 gigabyte file in this freshly created database. What's going on? It's like, well, it's not actually 4 gigabytes. It's 0. Here I show an actual example of creating a sparse file. So this example assumes that the file did not exist first. Call with open file for creation, and I call the truncate system call, which says make the end of the file out here. And so I say prepare a sparse bitmap file that's large enough to hold 1,000,000 bits. This function computes how many bytes it takes to save 1,000,000 bits. Turns out to be 125,000. So when it creates that file, if you ask for the length of the file, it's going to say it's 125,000 bytes. But if you actually do an ls-l on it, it's going to show it's 0 bytes actually allocated on the file system, but the size is still 125,000. That's a sparse file for you. So if you ever see that happen, that's why it's sparse. Okay. So in this slide, I show just verifying the fact that when you access a sparse file, a newly created one, when you read it, everything's zeros. And so I have a loop that goes through all 1,000,000 bits, verifies it. The getting function always returns nil for the 0 bits. Let's see. here's a call to we're going to set the first bit in the bitmap. And what I wanted to highlight here is the fact that after you're done running this function, you actually have 4 kilobytes allocated in the file now, because that's the page size of the system, and also the file system block size. I'm not exactly sure what happens if they differ. I would imagine it would be the larger of whichever. It would be the larger of the two. But the file size is still the same, because we haven't written past the official into file. And another thing I wanted to highlight is that to write that first bit, we actually suffered 2 page faults, one minor, one major. The minor page fault happened when we first looked at that page of zeros. The operating system actually had to do work to give you a bunch of zeros back and put them in your address space. And then when we actually touched the bit, wrote to it, the operating system considers that a major page fault because it actually had to ask the file system, okay, now allocate this disk space, and I will and put this data in it. So two page faults to set the first bit on the first page. Subsequent bits on the same page would suffer no page faults. Okay, downsides of programming like this. It's like C, but without the aid of static typing. It's easy to make mistakes. I've weirdly gotten pretty good at it, so I'm used to it, but it's really easy to make mistakes. The compiler's not going to help you. When you look at your program, you just see a bunch of numbers. All these align pointers are just fixed nums, or you just see a bunch of numbers. You don't know what they're pointing to, except for the fact that you have knowledge of the code. So if you crash, you need a backtrace, just a bunch of numbers. You're like, okay, and you got to figure it out. Explicit memory management's required. If you allocate something, you got to deallocate it if you don't want it anymore. So you can leak things. So you can mitigate some of these issues by using finalizations, but we've found in our experience that finalizations add their own problems, especially when you're multi-threaded. You could have a thread that you didn't expect to perform the finalization and cause very confusing problems. So this is a mixed bag, programming this way. It's also less...
Why not use the typing that you can with Common Lisp? So you can put, it's optional and nobody in programming Lisp does, but it seems like it would be valuable for you in this case.
Because it's not free. It costs. So, for example, we could make a structure that holds an align pointer, and that structure would have a type, right? Like say a hash table slot pointer, that has a slot that points to a hash table slot. Unfortunately, I'm overloading words here. If you can think of a way where it's not free, or where it is free, I'd love to hear about it. So we can talk about it.
Is in terms of space?
Space and allocation and indirection. So instead of having just the pointer to the thing, you now have a thing that holds a pointer to the thing. It's cost.
I won't take it here, but if you just wanted a validator where you basically just put types on things and you're just saying you can't stick a round peg in a square hole, then you're not changing anything.
I see what you're talking. We can talk about that.
Yeah.
Okay. Let's see. Blah, blah, blah. And additional downsides, it's less flexible. As you said, the sample data structures I talked about always held fixed nums. If I wanted something that held true 32-bit integers, I could do that, but it would be a lot slower probably. Your programming is less symbolic. Again, that's kind of the typing issue. You see this number, you don't know what it is. It's just low-level programming. You need to be mindful of cache coherence and memory instruction reordering if you're sharing amongst processes, which we are. Luckily, x86-64 has a very easy memory coherency model, but some other ports we're considering important too, or we actually have to add memory barriers and stuff like that. I'm not looking forward to that, but that's just the way it is. Let's see. That's it. So the future, ideally, we would be able to package this stuff up, make nice higher level interfaces that people can use, so they can take advantage of the features, persistence, shareability, without having to worry about how it's implemented. And that's it. So thank you for listening. If there are questions, I'll take them.
How do you store trees?
How do you store trees? Node has a left and a right pointer and a value.
The first structure you described,
The first one was a linked list, so it would be a linked list with an extra node, with an extra slot, yeah.
Yeah.
Does that make sense? So a tree is, I mean, you're thinking of like a binary search tree?
Oh, just a list with lists in it.
Oh, list with, well, okay, so, yeah, I didn't mention this, so I should have. I have it in my notes, but I didn't say it, so let me find out where I talked about that. Anyway, abort. Okay, I'll just talk. So in that F-list implementation, the value is a fixed num. It doesn't care what that fixed num means. You can assign any meaning you want. For example, it could be an aligned pointer to something else that's more interesting, a bigger object.
How do you keep track?
How do you keep track of?
If it's a pointer or if it's a value.
That was one of the problems, right?
Oh, sorry.
So as the person using this data structure, you know what you put into it.
Oh, got it.
Okay,
I
so-
understand.
Okay. Yes,
How valuable has this been for the final product that it's part of?
it's critical.
Critical, so without it, you were running too slow?
Without it, we had no way to have concurrency, real concurrency, 5 people doing queries at the same time and actually getting, 5 times the speed. It would be one at a time, but everything would be serialized.
So it was for the concurrency you did it as opposed to the speed of the presentation?
Mainly for concurrency, and speed is always paramount, right, when you're making
Not
it.
necessarily.
Can you pick on that?
Hardware gets faster and faster.
That's true. But, okay, well, yes, anyway, speed was very important to us. As you see, doing things one way, or doing things in a lower level way could get us a 5x speed up.
Because the other thing you gave up is you need to be on the Linux platform. You're not on Windows, you're not on the Mac.
That's right.
And so, is this different? This isn't all in your regular list?
No, you can't, doesn't, so that would be nice if we, ideally we would do
So
that.
this is a superset of regular Allegra?
You can look at it that way. It's a library.
What do you call it?
It's a library that we use to implement Allegra graph. So it's part of, from my perspective, it's part of our Allegra graph source code. It's not part of the Allegra CL source code. Does that answer?
So one thing after an earlier question, so I mean, if you look at PSX on your system, you see that you have, how many Lisp running on that system right now? Like 12?
A bunch, yeah. All performing various functions.
Is there like a master?
A master process?
Yeah.
There is. There's a master process that forks all the other ones.
So if you had like five people trying to do 5 different updates or something on a Lego graph at the same time, what happens? How does it manage
So
conflicts on this data?
okay, so let's say we have 5 people doing queries and whatever. So they'd each have their own Lisp. They would each say open triple store, and what that would do is figure out where all these mapped files are. There's a directory that has them all. It would map them and start accessing the data. So for example, if you were adding triples, what it would do is accumulate the added triples in your heap. So my heap would be different than Jan's heap. He's adding triples too. He's adding his triples to his heap. I'm adding them to my heap. When he commits, then his private triples go into the shared space.
It's just whoever gets there first.
Whoever gets there first. Yeah, so our commits are serialized. Reads are concurrent.
Okay. And you're saying you had some functionality for like kind of having a private space to work on stuff that's not interfering with everyone else, and then things like that.
That's this thing. We have one. You can have a shared version where you have one web server sitting waiting for calls, and they all go on the same list. But for anything interesting, we recommend that you get your own list. So just try to graph the tool I showed you on the web interface or in your Lisp interface. You just say, oh, in Java, I want my own session, and then you get your own Lisp on the box, and you're in your own world. Only when you do a commit do you talk to the rest of the system, where you, well,
Any other questions?
You mentioned parallels of like 5, but I assume the goals of of this whole thing are a whole lot more than 5.
Yes.
Oh,
So I
yes.
assume it scales with the file system and 500, 5,000.
We found it scales pretty well.
Yeah.
I've been
What's
happy.
the largest parallelism that you've done?
That's a good question, Jans. Do you happen to know what our bigger customers do?
Customers have done tests where they simulated 500 users at the same time. They don't get 500 Lisps on the system. They all go through the web server. So we have, like, you can see here, how many backends do we have here?
There's only one showing, but there could be.
But if you get more requests,
10.
we say, oh, we need a new one, so you start a new, so.
It's a pool of
too many
workers.
people, It's
Yeah.
a pool of backends, and you expand the pool if there's more requests, and then each backend can handle 10, 20, 30 people all asking queries. But within that server, queries are serialized.
But in the end, you're serializing over, you're assuming that the center of it all is some kind of network attached storage, which you're getting to through memory mapped I/O to a drive. So in other words, if I were to put this on AWS, I would end up bottlenecking, unless I did some kind of sharding tricks, I would basically bottleneck at the place where, okay, you can't get another processor to talk to one shared network attached storage device, and it's over at that point. That's the scaling that you get to with this kind of approach. Am I getting it right?
Yeah, as with most databases, once you start accessing the disk a lot,
But
You're
the
gonna
disk
block.
is the centralization point, is my point.
Yeah.
The way you've designed this, you could probably re-implement your foreign interface to be on some kind of other substrate, but right now, it is on the disk, and so you can only get as parallel as you can get processors attaching to one disk. Am I getting it right?
if you're memory constrained. So if you memory map a big file and you start accessing it, if the file's resident in memory, it's not reading from the disk every time you're accessing.
No, if I wanted to have 1,000 servers that were
1,000
serving up
servers,
the
yes.
same triple store,
So we do that differently. In that case, you'd run multiple. Usually what we'd do in that situation is we'd say, okay, you run several systems, each with their own local storage. And then
And there's some kind of update scheme that goes between.
you'd issue the queries to the right leg graph. Jan's described some of the partitioning schemes that
That's the
might be
other
used.
thing we do. You can do replication.
I see, okay.
And so if you say you want to work on one database, so here's the thing, I mean, there's so many answers to the scaling answer.
Yes.
We can take the rest of the evening, but one, that works really well if you have, say, several billion triples, but you need too many people talking to it, you create replicas, and then for queries, you talk to the replicas.
Okay.
For updates, you go to center one.
Right.
Another story is where they talked about the healthcare thing, where we just basically partition data. Yeah? And then I can tell you all our intelligent customers run on machines that, I mean, you don't want to know how much terabytes of RAM, you know? That is, and 96 processors or whatever. It's just like, I mean, the world's, everything on the web is in memory anyway. I mean, you know that. It's a little secret, but everything runs in memory anyway. So we have for us too, our customers buy huge, huge machines. And I'm thinking even having a banner on the product, spinning disk forbidden, you know, because the only thing that really works is you really need or really, really striped disks or solid state drives. But everyone is going solid state drives anyway. Because we have still a lot of random access too. That's the problem with graph the difference between graph databases and relational databases. We have far more randomness that we have to deal with than relational databases. So, yeah.
Kind of on the subject of randomness and so kind of going back to the level that you were talking about, the use case of like the data lake.
Yeah.
Let's assume you have like 10 data sources and 10 different analysts, and that some analysts need to do a query that requires like getting more data from one of the data sources that breaks that like local schema for the rest of the analysts. How would you handle that case where 10 different data sources, it's like multiply your chances of any one of them changing by 10?
Ask the question again.
Okay, I'm saying you described the data lake of taking many data sources and making them available to many people doing different types of
Many data
queries.
sources.
Yes.
Yeah, about patients.
And so
We partition all the triples for patients. So one patient goes uniquely into one Allegra graph. Yeah, so you cannot find any triple about that patient in any other one.
okay,
So there's no problem. You can, when you do a Sparkle query, you basically go to every database and say, because you can partition all patients, and then give me the result spec. However, sometimes that doesn't work because you need to have the brother of a person, which undoubtedly will be in another database. Now you have to use a thing called federation. Okay, it's much more map-reduced way of doing it.
my question is about schema change. Schema changes.
Oh,
on the
schema
data
changes,
source.
yeah.
There's no schema.
Like if you will, quote unquote schema changes. That if one of the data source decides to update how they're doing, and then you have all these other people that were making these really complicated queries, going into all these different data sources,
No, we
and look, one of them changed.
We show people that want to make schema changes. I mean, we have one unified clinical event model, a model that describes everything can happen to a human being from birth to death. We have 350 types, and everything that we have so far fits in it. But you make a very good point. At some point, someone wants to add something to the schema. Yeah, like for example, we have now the machine learning that we feed back in the data lake. That is a new schema. That's the only way to do that is to, well, only one person is allowed to do that. That's not different from relational databases. But for us, it's much easier to add new stuff. So I can start with the fresh Allegro graphic and say, Jans lives in Moraga. Moraga part of East Bay. East Bay part of Contra Costa. Contra Costa part of California. Yeah, California has population. I have not said anything about the schema. I just dump the data in there as triples, and I instantly can say, give me a person that lives in a place, in the place, in the place that has so many people. Yeah, I never created a schema. I just added triples. So it is very flexible what we can do. So a researcher could just add their own data. The problem is, Spider-Man with great power comes great responsibility. Or the other one about shooting in your own foot. It's very easy to add your own little private world, and then no one else will ever know about it. So you have to have discipline in this case. Although it's easy, you better.
So you treat it like a social problem.
Yeah, it's a social.
It's all about limiting authority.
it's all about it's a social problem. Yeah.
We have pizza.
Yeah. So at the point we have pizza. So I would suggest that for the lightning talks, apart from the person doing the talk, we eat pizza. Okay.
Yeah.
So thanks again for this.
Thank you.